Hello everybody and welcome to this session. Today's topic is GPR surveys through water, or sometimes some people refer to that as WPR, water penetrating radar. But to do this we need to have a look at a few considerations on this application. We have to look at some limitations and I have some data examples, a few case studies a little bit later. First of all, my name is Mike Langton. I am the Senior Applications Engineer at Guideline Geo. Guideline Geo manufacture the Marla brand of GPRs, and you can get like I say, you can gain lots of information on our website, guidelinegeo.com, and you can see our range of products there, including other systems from our sister brand ABM. So to start off with, I'm just going to go through a quick theory session. And to do this, I need to look at the basic land-based surveys and how that applies then to water-based surveys. So let's first of all take a look at a standard shielded antenna. And to do that, I'm just going to peel back the antenna itself to have a look at the components within that antenna. On the left-hand side, we have the transmitting antenna, or TX for short. On the right-hand side, we have the receiving antenna. And what we do with the system is we send a pulse of energy electrical signal down to the transmit antenna, and that will convert that into a pulse of electromagnetic signal or a radio wave. That will start to expand outwards from the TX antenna. At the point that we launch that signal, we start to make a recording, a measurement on the receiving antenna. We tell the receiving antenna, in effect, to start listening. And we will start to record a trace along a vertical axis, in this case, from the start point. And in effect, this is time zero right at the top. So as time goes on, that signal, that electromagnetic pulse of energy, will start to expand out from the transmit antenna. And you'll find something quite interesting will happen initially. You can see here we have two wavefronts appearing. As time goes on, you'll see this expand outwards in a more exaggerated fashion. But this section of the wave is often referred to as the air wave. It's a signal that's traveling directly between the transmit and receiving antenna. Now, I have separated them out quite extensively here, but typically they are actually quite close to each other, the transmitter and receiving antenna, but the actual antenna lobes themselves, there is a bit of a distance between the two. So we get this air wave traveling directly between the two. Sometimes this is referred to as a direct wave. We also have this wavefront here, which is traveling through the ground. Now, one of the key things here, you'll notice that the air wave is starting to break away from the ground wave. And the general thing here is that the air wave is traveling faster than the ground wave. This will be different. The ground wave will be different. The velocity of the ground wave will be different in different situations and different soil types, but typically this is traveling much slower than the air wave. So the first thing that's going to happen is the air wave will pass through the receiving antenna and we'll get response from the system. And this, you can see here, is a kick on the response on the trace itself, often referred to as a wiggle trace for obvious reasons. Whilst this has been going on, the ground wave is traveling through, obviously, the soil. It's expanding outwards, so there's going to be some natural decay of energy, but also the soil itself will attenuate that signal in different ways. But typically, this signal will be reduced, attenuated due to the soil conditions and other contributing factors, which we'll look at shortly. As time goes on, then continuing, then the second thing that's going to really respond on the receiving antenna is initially a little bit of the ground wave passing through, so we get a secondary kick on the trace here, lower amplitude because the signal is decayed, it's attenuated at that point. Whilst it's all been going on, part of the energy that's been traveling through the ground, only a small percentage of that has hit a target. Where we get a change of electrical properties between two materials, and particularly a significant change of electrical properties, that will cause a reflection in some or all of the energy, depending on what that object is. But part of that energy in this case is being reflected back from this target. And as time goes on, nothing's happening at this point because nothing's been received at the antenna here. But then eventually that signal will be reflected back to the surface and we get response on the receiving antenna, and we get a small kick on the trace that you can see just there on the left hand side. So this is a measurement, one single measurement of a signal into the ground and recorded at the receiving antenna. We're going to convert that into an image, typically a grayscale plot image. And you can see here that the grayscale, everything that's going to the right or a positive signal is going lighter grey to white. Anything to the left is a darker or going to black in effect. So the bigger the peak, the lighter the colour to the right in this instance. So we're going to a white response there. So as the radar moves forward at set intervals, we're going to shoot the signal into the ground and take a measurement. And that will build up our typical 2D radargram. Distance across the top and in effect time down the left hand side at this stage, because we're just measuring time. How fast the signal's going to get there and back can then be used to convert to depth, but typically GPR is going to measure based on time, but we can convert that to depth if we know what the velocity of that soil conditions are. So if we take a look at the typical velocities, there's going to be three that's probably worth remembering. First of all, air. As an electromagnetic pulse of energy travels through a vacuum or air, it will travel at or very close to the speed of light, and that is 300 meters per microsecond or 30 centimeters per nanosecond. If we take an average soil value, this is average, there are factors that can cause this to be different and change to be either increased or decreased from this value, but a typical value would be 100 meters per microsecond, or around 10 centimeters per nanosecond. The third value that's worth taking a note of is water. Water velocity is approximately 33 meters per microsecond or 3.3 centimeters per nanosecond. So if we take soil, that's traveling about a third of the speed of light. If we take water itself, it's about a tenth of the speed of light. So it's a lot slower. That really needs to be taken into consideration when we're working with the GPR, and particularly what sort of depth we can see, and also what sort of time window you're going to set when you're collecting your data. So a much wider time window is needed, typically when we're measuring through water. Some other considerations for water-based measurements we need to think about is the actual boat itself. The boat needs to be a single hull construction. Double layers can cause or create ringing in the data, and this can disturb the depth penetration or the water penetration itself. So if you have a large air gap between the antenna and the water itself, the air to water interface will cause a large reflection in the data and will also cause ringing in the data. We can also get some of that energy passing along the actual surface of the water itself, and this can then cause reflections from objects that are above the water, maybe like trees on the shoreline or buoys that's in the water itself. So double layers also to take in consideration needs to be plastic or rubber type material, non-metallic material, otherwise the signal will not pass through. If you have a double skinned boat, one of the things that I've done there to get around that is actually to place the GPR antenna itself into a rubber dinghy, a small rubber dinghy. Get that antenna as close as possible to the water itself, almost in contact with the water in effect, to maximize that energy into the water. The quality of the water itself needs to be taken into consideration. And what I'm talking about there is things like the amount of dissolved solids and the conductivity of the water. Example, if there is a large amount of suspended solids within the water itself, you can get sometimes that will increase the conductivity. And of course, salt on salt water, briny water, the GPR will not work in that situation. So it has to be fresh water, lake water, canal water, and that type of water rather than salt water itself. Also, we need to take in consideration the measurement lines. When we're taking lines, the profile lines, the measurements itself, we need to take that into consideration from a point of view. If you take a look at that image on the right hand side, the beam of the signal increases as the water depth increases. If we're looking for an object, we may need to pass multiple times at relatively tight spacing depending on the depth of the water. And there is an equation to calculate this, which we'll discuss in a second. But the key thing here from this is to remember that the footprint in water is much smaller than in other geological material. I've got an example, a worked example of that in a second. But the antenna footprint will vary, will be changed. This beam of signal, in effect, that's underneath the antenna itself, will change depending on the material type that the signal's passing through. So there's a few factors that we need to take into consideration here. We just look at the wavelength. That's the lambda sign. We're looking at a quarter wavelength in this equation. We need to know what the depth of investigation is going to be. And then we also need to know what the relative permittivity of that material is. And the equation is E minus 1 square root on that. So depth divided by square root of E minus 1. Just a quick note on this. Typically, we're going to move along the x-axis with the antenna. So you'll find that as we're moving forward with the antenna in the typical configuration, that the footprint is wider front to back than it is side to side on the antenna itself. So wavelength wise, one factor to take in consideration. You can get these charts readily available quite easily, but you'll notice here that this is just in air, and the equation for wavelength is velocity divided by frequency. I'm talking about the signal velocity here. So when we're looking at signal velocity, then typically with water, remember that's 33 meters per microsecond, 3.3 centimeters per nanosecond. That's the value I'm going to use divided by the central frequency of the antenna. And this is an approximation. It's not an absolute value. The things that can change this, but just to give you an idea of the antenna footprint. So when we're looking at the wavelength, take into consideration the velocity of the signal and also the relative permittivity. I've got a chart here of typical values, and you're going to notice there that the relative permittivity air, and that's what we're referring to, what that is the relative value, is 1, or vacuum is 1. Freshwater, you'll notice there's very high value. This is one of the contributing factors to the limitation of GPR in water, depth penetration, and some other factors. So to take those values and just punch that into a worked example, I've taken an average soil with a dielectric of 20 as a rough average and a depth of 5 meters. I haven't shown the workings out here. That's one of the golden rules, I guess, I've just broken. But the value of A of the antenna footprint here is 2.15 meters, and B is 1.075 meters. That's just the radius at that point. If we compare that against water, then looking at that with a dielectric of 81 and the same depth value at 5 meters, then the footprint is considerably smaller. And this is one, like I said, one of these contributing factors to looking at, maybe if you're looking for objects, how often you need to pass over the area, particularly if you don't know exactly where the object is and you're trying to define its position and maybe the depth of it, etc. So you have to do a lot tighter spacings between profiles if it's an object. If it's just general lake bottom bathymetry, that type of application, then you may want to do, or you can do wider measurements than that and just take spot measurements across the area. Right. So we need to take in consideration the difference in velocity, the groundwater. That's quite critical when we're taking measurements on water-based surveys. Remember one thing that the antennas can resist, the Marlow antennas can resist rain and water puddles or pools, but cannot be submerged without additional modifications. They are not submersible proof in a way. They are weatherproof, but not submersible devices. We need to take into consideration the trace interval. How often we're taking the measurement along the line of the profile. That may need to be adjusted to the speed of the boat or the drone, or the wheel. If we're taking measurements on ice, sometimes we're going to measure the thickness of the ice and maybe the water below the ice. In that case, we can use the measuring wheel. But if we're working on water itself, typically we're going to be measuring with time triggering. So we're going to set the triggering for the pulse based on time of a set value. So depending on the speed of the boat, depending on how often you're going to take the measurement, will vary. A little bit of experimenting will be needed to get used to the values and also the speed of the boat that you can travel on the actual surface of the water itself. So some of the typical applications then for the water-based surveys, typically bathymetry is very popular. The amount of sedimentation, silt layers that we have at the base of the water, the lake or the river. The actual shape of the bottom, a bottom survey prior maybe to utility installation, maybe looking for obstacles and that type of thing. So geological layers like soil layers and bedrock we can look at, and also mapping of objects, and this could be things like protruding stones. I'll explain this a little bit later. For the car industry, I'm talking about when they're taking testing in and around cold areas and measurements on actually on driving the cars on ice lakes, etc., or on ice. Things like UXOs and weapons and other metallic objects that could have been placed, thrown, or dropped into the water. So initially, we need to look at the water type. Fresh water is good. Salt water or briny water is bad. And that includes maybe an estuary where there's a certain level. You could have a mixture of fresh water and salt water in there, maybe even layers of salt water and fresh water. But any level of salt is bad. That will increase the conductivity of the water to a point that the signal will be absorbed and won't be able to actually get any decent or reasonable depth penetration. And that can include maybe around rivers and lakes where we have agricultural activities nearby, runoff that will increase conductivity, things like cattle and horse farms, and if there's any sewage treatment plants nearby, this can increase the conductivity of the water, which will affect effectively the depth penetration or the ability to actually see into the water. Frozen lakes can make the deployment of the system much easier, but problems can arise through layers of ice and water. So we need, ideally, if we're working on ice, nice, solid, cold ice without puddles of water or layers of water in between. Secondly, we need to take into consideration the target type, and that may be how we define the instrument choice. So we're looking at target size, target depth. Is it sufficient to just do 2D, or do we need to do a 3D survey? Remember that the footprint is much smaller in water compared to ground construction. And thirdly, how do we get the system out there? We can, of course, wade if you've placed the and turn into a small rubber dinghy. We can walk through the water if it's not deep enough. One thing to think about there, though, is if you are walking very close to the antenna, you may see reflections from your body, your legs, your feet in the data set. So if we're going to do that, considerations need to be taken into an account. And quite often I may pull the boat behind me on a rope, if that is the case, just to get away from your physical body itself. As I've said, the boat design we need to take into consideration, and the antenna position within the boat itself. And quite often, like I said, floating the antenna could be an option. And I've got a couple of options with that a little bit later when I show you the case studies. And of course, we could, and this is becoming more and more popular now, use or utilize a drone. There are some drone mounted GPRs available now that you can use, but obviously these could be limited by legislation. You need to check out your local legislation to whether that is allowable or not. One final thought really on survey considerations is the positioning. So the positioning of the data itself and the measurements, and this typically can be used by different options. The easiest and quickest I would probably say is the GPS. We're in quite often open areas, and GPS can be quite effective in that situation. So GPS or GNSS for positioning the data. We could use a total station maybe if the GPS isn't effective. There are things like time triggering and some alternatives for positioning to take into consideration as well. But like I say, typically, quite often I'm going to use GPS or GNSS for the positioning of the data. So when it comes to once we've collected the data, we need to look at the data processing and some examples coming up here. First thing we need to think about on this one is complications from things like positioning of the data. Unlike on land where we can take physical lines and measurements from the surface, we cannot do that on water. So we need to take that into account. Take into account the water column itself, things like the depth, this water conductivity. We need to set the correct velocity. The nice thing about water is we can quite often measure the depth of the water quite easily. You can drop a weight and a rope or a string, and we can look at the depth, and we can look at that value in the data set, and we can correlate that to the correct velocity quite easily. And if we're going to use a drone, then we have to take into consideration the height of the drone above the water. We need to normalize for slight variations in the flight height of the drone, and that can be done in the post-processing stages. So I've just taken some raw data. This is a raw data from a 50 megahertz rough terrain antenna, or RTE. You can just see some of the reflections there. First of all, I'm going to apply some linear gain, some exponential gain, a combination of both of those to the data set. I'm then going to apply some bandpass filtering as well. It's quite important that we apply some bandpass filtering to the data set. And finally, one thing that quite often you need to do is to apply a background removal filter. Even though we get in close proximity to the water, we can reduce the ringing effect in the water. You will still see a high level of ringing in the data from the water column itself. So again, gain and background removal in this case has been applied. We can still see some effects of the ringing within the data, but that's been decreased considerably with background removal. So typically, gain, background removal, and bandpass filtering will be applied to the data set when we're looking at that. And obviously, we're looking at differences in height from the drone if you're going to use a drone. Next part then we need to take into consideration is the interpretation of the data. We can look for discrete targets, we can look for horizons, and you can see here we've picked out a target in the data here, and we can also pick out the horizon from the lake bottom quite easily. And And even just taking these measurements from a simple text table or value of table from tables, we can do some fancy 3D plots there on the right hand side with the processing. You can see here the path that we've taken for this survey here. We're just going to take spot checks of the value from the tables around this area to plot out and convert that into a 3D plot. So some case studies then. If we take a look at the first one, we're going to have a look at some objects in this instance here. This is a recreational lake. And what had happened here is an object had been thrown into the water, been discarded, and that object needed to be found. The lake itself was approximately up to 3 meters deep, so not that deep, typically around about 1.5 to 2 meters deep. So with that in mind, we took a 450 megahertz antenna from the Ground Explorer range of GPRs. We found that the 450 megahertz gave us the correct level of depth penetration and resolution in this instance. The position for that object was just needed to be an approximate value, not an absolute value, because eventually the divers would have gone down into the lake to find the object. So just a rough positioning. For that, then we use the internal GPS that's built into the Ground Explorer. And we use the time triggering to trigger the GPR itself, and this was 0.1 second. The boat was running quite relatively slowly for this value. Obviously, we used a plastic boat, and this was a single hull boat. This one. This is how the data looked. You can see the route. This was just one of the first test runs that we did, looking for the object. We calculated. We knew what the object was that was thrown into the water, and we took the same weight of a similar object and we threw that on the land to see how far we could actually throw. A typical person could actually throw into the lake. So we could calculate. We knew at what point roughly the objects had been thrown. So then we could calculate roughly the distance. So we either go around on the boat at that position. And at this position here, we can see the sedimentary level at the bottom of the lake, and we can see the lake bottom itself. There is a point where the lake goes deeper and we'll lose that measurement because the depth of penetration now has gone beyond the ability of the GPR through the water level. But we can see a hyperbolic response within the data, and that was marked with this marker above it with the GPS position taken from that marker. So we can see there that the object had actually gone into the silt. It actually sunk into the silt. It was heavy enough to actually disappear into the silt itself. And that's one of the abilities for the GPR, is that it's able to see actually into and through the silt levels or layers. And in this case, we could see the object. Second case study then we're going to look at is sedimentation. This is a measurement near to a water power plant. So here the water itself is dammed, and that is going to be used for powering the generators for the electrical generation. So it's quite critical in this situation here that we need to look at the levels of sedimentation. We need to look at the amount of water that can be held within the lake, and also it's critical for dam construction itself. That can be taken into consideration. We used a Marlow X3M /Pro X with a 100 megahertz shielded antenna, and you can just see there it's in the bottom of the boat. We used a GNS for positioning because we wanted accurate position of the data, and in this case we used time triggering at 0.02 seconds. That meant we could go a little bit faster. We could take measurements a lot quicker, so the boat could actually travel a little bit faster than the previous example. But again, single hulled boat, plastic boat. So from that, we could see the sedimentary layers easily identifiable above the firm dam bottom, as well as stones and boulders and rocks and outcrops of the lake bottom itself. And in that, GPR aided in the estimation of the volume of sediment and also the visualization of the actual lake or dam, reservoir, etc., the actual base of that quite nicely. This was plotted into a nice 3D image that you can see on the right hand side. We can also look at another case study and looking at the condition of the actual river in this case. And this was important because in this case, we were trying to, or it was prior to installation of a new water pipe. So we're going to lay a water pipe along the base of the river itself. So we need to clarify the condition of the base of the water. So we used in this case, a Marlow GX 160 megahertz antenna because of the deeper depth in this instance than the first example. Again, time triggered at 0.02 with the aid of a GNSS as well for the positioning. And in this case, we used an inflatable rubber dinghy, which are quite effective because quite often the base of those are quite thin compared to a double skinned hull. So plastic boat, single hull, and several parallel lines were made over one measurement, one profile. So moving backwards and forwards several times over the planned route of the water pipe installation. You can see on the left hand side, these are all the runs. So we can see the water level dipping, going deeper depths, and moving back towards the side, and then turning around and then moving back towards the central point and back across again, so on and so forth. That's just one measurement across the strait itself. So we could see here we had firm bottom with just a few boulders that were imaged, these protruding sections that you can see, very little or no sedimentation, and most likely till moraine underneath a more sandy material in this instance. Another case study was for boulders. Here we're looking for objects that may be protruding close to and near to the surface of the water. In this case, this was going to be a frozen lake that was going to be used in winter for testing cars. So the car industry quite often uses frozen lakes for testing the cars in cold, frozen conditions. But we got to take in consideration that there may be obstacles in or very close to the surface, and we need to avoid hitting those when we're taking those measurements, because you can get the ice layer and then snow layers above that, and these can be hiding objects very close to or near to the surface. So the measurement was made on ice, and it was towed behind a snowmobile in this case. And you can see here instances of protruding rocks or boulders, and these were mapped out across the area and marked on a map that you can see on the right hand side. That one. Another case study to look at is a lake bottom. Again installing a water pipeline. We're looking for smooth bottom condition, or the conditions of the actual lake bottom itself. Now, one thing that we used here, and the one reason why I'm sort of looking at this case study, is that the device that we used, the GPR in this instance, was the Pro-X with a 50 megahertz rough terrain antenna, so lower frequency. Higher frequencies were not suitable because of the lake depth, reservoir depth in this case. And what we did here is we placed the RTA into a plastic tube. We sealed off the tube, and then that was towed behind the boat. So the measurements of the GPR is actually inside this plastic tube on the right hand side. Again, we measured, we triggered the GPR based on time, and GNSS was used again for positioning the data. The offsets, though, that we encountered, because the GPS was on the boat and the GPR antennas were behind the boat, several meters behind the boat, that offset was taken into consideration during the post processing. That's possible with certain types of post-processing software. We can actually apply an offset from the GPS to the GPR. But we could see quite clearly there were objects and protruding outcrops of rock in the data set from the data that you can see here quite clearly. It's quite easy to see these and mark these positions of these outcrops, this data set. And then finally, I was going to look at an application that I mentioned earlier, and that is for mounting the GPR on a drone, or what we refer to as the Geo drone. And this was one of the early tests that were made of the Marlow Geo drone. It's an 80 megahertz antenna. The aim here was to map the bathymetry, or the water depth, from an airborne platform rather than within a boat. So this is the Geo drone mounted on a DJI Matrix 600. It needs to have a lift capacity, and in this case of around 5 kilograms for the weight of the GPR. So a continuous profile was taken in a circular pattern around the area, one long continuous profile, and we can see the lake, the river bottom in this case. So the riverbed here highlighted in red. The riverbanks moving towards the riverbank and then moving away from the riverbank in the lighter and darker blue, and repeated again. Further down, we'll turn around and move the drone back towards the riverbanks. So from that point, we could see this sediment structure, and measurements were taken and then plotted into a 3D model that you can see here. And one other unusual one that I just wanted to just mention was not the case of GPR on or through the water. It was actually a case of GPR in water. And this is from our friends down in Australia, from Marlow GPR, Bill and James, who ran this project. And this was purely just to look at a tunnel that was underneath this reservoir, internal reservoir here. So they waterproofed the antenna, placed that into a fully submersible box. All the connections, the pulse encoder, etc., were waterproofed. And this is not an easy undertaking. It takes quite a bit of engineering to accomplish this. So there's a lot of consideration to take into account here. But purely was just to look at a proposed new tunnel beneath this construction here. So just to finish on a slightly lighter note, going back to that recreational lake that I mentioned earlier, one of the key things that we did actually find in this lake, it wasn't intentional. We weren't too sure at the time that we did actually come across this, but with later reports, we did find out what was actually in the bottom. This is a very typical ice cream truck or ice cream van, and being a recreational lake and people walking around there, you can find these quite often around the recreational lake. But in this instance, the handbrake, the emergency brake had failed, and it had gone and dropped into the water. And if you've ever wondered what an ice cream truck or a vehicle looks like in the water, that's how it looks in the radar data itself. So just a slight lighter note to finish off with. So with that in mind, I'd like to thank you for attending this session. Please do drop us an email if you have any questions. This is just some of the team that you can see here undertaking an activity a few years ago. But yeah, drop us an email. You can go onto our website and there is an inquiry form there if you have any questions or have any queries. That will generate a support ticket for you and we will respond to that. But with that in mind, thank you very much for listening. I hope you enjoyed that. And that is the end of this session. Thank you for attending.